And I'll get my whiteboard up and we can start learning some new stuff. Maybe before we start, I'm going to do a little poll. Okay, on a scale of 1 to 5, 5 being the most, 1 being the least. I normally do this 1 to 10 in class, but this poll lets me do 5. So 1 to 5, what is your energy level today? So 5 being the most, 1 being the least. Emily, do you have a question? Okay, so we're looking for one more response. Your energy level today on a scale of 1 to 5, 5 being the most, 1 being the least. Okay, here are the responses. This is for the benefit of people watching it at home. We have 2 people with a 4, 7 people with a 1, and sorry, 7 people with a 3, and then 1 person each with 1 and 2. So okay, that's good. I'm particularly glad there's no 5s here because that means no one's having a drug problem right now. So that's really good. People who are at a 4, you know, have pretty high energy. People who picked 3, you just don't want to be below average, and the 1s and 2s, you know, 1, you barely had the energy to click 1. Okay, good. So we know we all have some energy in varying degrees, but I want to talk today about what is energy exactly, because we all know when we have energy. We know if we can give a number. Everybody voted on this one. We can vote that we have energy, but defining what energy is exactly is not so easy. So textbooks take a lot of different approaches to defining energy. And the reality of it is we don't actually know what energy is, not really. We don't know what it is. When you say you are high on energy, what you really mean is that you're not tired. And when you say you're low on energy, you're saying you're tired. At least that's what I think. I think that's true for most people. Raise your hand if that's accurate. What you were really telling me is how tired you are. That's what I was doing when I voted. But what is energy exactly? So some books tell you honestly that it's something mysterious. We don't know what it is. It's neither created nor destroyed. It only changes hands, it changes forms, so it's continually changing. That's what we saw in the lab exercise that you hopefully all were able to do. Energy can take many forms. We are going to be primarily talking about mechanical energy. And I'll make that more precise as we go. But there is also chemical energy and electrical energy and thermal energy and, you know, lots of forms of energy. So just take, for example, you know, if you do a hard job, someone tell me an example of hard work. Okay, well, give me an example of something that's hard work. Ziad?
Lifting weights.
Okay, so good. Lifting weights. Can someone give me another example of hard work? I know at least 2 of you are working hard because you don't have any energy. maybe 9 of you are working. What else is hard work? I know some of you guys do hard work because you send me emails telling me you're working so hard on other things you don't have time to work on physics. So what's hard work? I need a list. I want a list of lots of stuff that counts as hard work. Dustin.
Construction jobs.
Okay. Can you be more specific? All construction jobs or just some construction jobs?
Pouring concrete.
Okay. All right, someone else. I'm just going to start calling people. Blair, you're the first on the list. What's a hard job?
A sport like basketball takes a lot of energy.
Okay. Emily, what's a hard job?
I work at Chick-fil-A, and that's hard work. Going outside in the heat.
How do you spell Chick-fil-A? I know it's kind of weird.
CK.
CK.
Yeah, and then FILA. Yeah.
Like that? So
Yeah.
Dash?
Yeah.
Okay. Chick-fil-A. Working at Chick-fil-A. Okay, Grace. What's hard work?
Running.
Running. Okay, and Haley.
I would say, like, I work at the winery. I'm like lifting boxes of wine and stuff. That's hard work.
Okay. I'm glad you clarified, because if you just said working at the winery, I'm imagining you're just on the terrace sipping wine and you're a sommelier or whatever that's called, and that sounds like you should pay them. Okay, but lifting boxes. Joseph, what's hard work for you? Riding a bike. And Kat.
Doing yard work.
Okay, Maria.
Mine was yard work.
Okay, and Stephanie.
I was gonna say like when you're playing tug of war and you have to pull on the rope.
Tug of war. Okay. So great. These are all examples of things that make us tired. So energy, let's say we're lifting weights. What's happening with energy? We start off by eating food. The food represents chemical energy. And when we eat that food, the food is changed from chemical energy into some thermal energy. When we lift weights, we get hot, our body temperature goes up, and then mechanical energy, the actual lifting of the weights, moving the objects. So there's 3 forms of energy. If we're pouring concrete, we have, the truck has gasoline, which represents chemical energy. It's burned, that turns into thermal energy. To generate power. There's electrical energy in there, that process as well. And then the actual pouring of the concrete and the spreading of the concrete to fill the forms, that's mechanical energy. In basketball, starting with your own chemical energy, you're burning a lot of calories as you run around. That energy is being transformed into heat energy primarily, a little bit of mechanical energy. Working at Chick-fil-A, that's probably mental stress energy. That's not really a form of energy in our class, but you're like moving constantly and being stressed. And so I don't want to go through all of these at this time, but I am going to talk about them all. All of them represent transformations of energy from one form to another. Now, this sort of ineffable substance, this energy, this indescribable thing, we can't really see, hear, smell, taste, or touch it. We just know when we have it, we know when we lose it, and we can sort of see and imagine how it's changing forms. And because it's so hard to define, textbooks often take the following path to define it. They say energy is the capacity to do work, which is why I wanted to talk about what counts as hard work. But unfortunately, what is hard work in English, which is what you guys just told me, okay, isn't necessarily the same thing that the physics book means by work. So just to give you an example, lifting weights would count as work, pouring concrete counts as work, but playing basketball barely counts as work, even though, Blair, I would get more tired playing basketball than pouring concrete probably. I mean, I couldn't play basketball for 10 hours or 12 hours a day. I probably couldn't pour concrete for that long either. Working at Chick-fil-A doesn't really count as work. Running doesn't really count as work, but lifting boxes does. Riding a bike, maybe it depends where you're riding. Yard work is, there's a lot of different things that could be yard work, but some of those things would involve hard work. And tug of war, you know, it depends, but probably if you're playing tug of war and you're moving back and forth a lot, then it's hard work. Okay, so we got to try to find some unifying idea here. Why some things are hard work and some things are not. So in English, they're all hard work. I wouldn't dispute a single one of these. Okay, every one of them can make you very tired, and that's usually what we mean when we're talking about something being hard work. That's why normally there's like this one person who says physics homework is hard work, and they get irritated when I say no, it's not hard work. In the same way that you might get irritated if I say that your hard work isn't hard work. So what exactly is hard work? What do you need in physics for there to be hard work? So there's really three things we need. So work must include the following things. Okay. The first one is there must be a force. Okay, there has to be a force involved. The bigger the force, the better. Okay. So some of these probably all involve force, although maybe depending what at Chick-fil-A, which jobs you're doing may not require so much force. It may be more about, just hustling and moving around a lot. There must also be doing homework definitely doesn't involve force. There must be a displacement. Okay, so there must be a force, there must be displacement. The more displacement, the better. That's why tug of war, if you're playing tug of war and neither side is winning, you're just pulling as hard as you can and getting nowhere. The other side's pulling as hard as they can. Even though there may be tremendous forces, if there's no displacement, there's no work. Okay, and the third one, this is the most subtle. And so I'm going to say it in a way that I think helps you remember it, but it's not a technical thing. I'll make it technically accurate in a minute, but the way I like to say this is, I'm going to put quotes around it because it's not a literal statement, but I say the force must be responsible for the displacement. Okay, the force must be responsible for the displacement. Now, that's not really a literal statement because we know that objects in motion stay in motion on their own. So you don't need a force to keep something moving. It's just going to move all on its own. So I'm going to give you an example to show you what I mean. So imagine you're driving in the car. Okay, and so this is an aerial view of the car. the tires and the roof of the cars here. And you run out of gas, and so you get out and you start pushing the car. Okay, raise your hand if you ran out of gas. Maria, Dustin, a couple people. Raise your hand if you ever just broke down. Your car just stopped running. You didn't run out of gas, but it stopped going. A few more people. Okay, so you've been in the situation. Your car's in the road, and you got to get it out of the road. I like running out of gas because maybe there's a gas station, 50 yards down the road, and if you can push it to the gas station, you can get going again. And if it just breaks down, you pretty much, not much you're going to do about it, depending on how good you are at fixing your car. So suppose you're pushing the car, and I'll use green for displacement, and so there's a displacement over some period of time. We can call that delta x. Maria. Maria, did you raise your hand? Was that an accident?
Yeah, that was an accident.
Okay. So you're pushing, there's a displacement, and everything's good. You're doing work. Okay, you're doing work. Now, suppose somebody comes up and they see you pushing the car, and they decide to help you. So they come up and they start pushing the car with a force F, like that. What do you say to this person? Keeping in mind that we are recording, so keep it reasonably polite. What would you say to this? Anybody? What would you say to this person if they came to help you push your car to the gas station? Are they helping you? Kat?
I would tell them that they're doing it wrong.
You tell them they're doing it wrong? Okay. See, me personally, I'd probably just say, thank you, sir. I think I've got it. Just I don't know what this person is thinking. Why are they doing it wrong?
Because since they're just pushing on the side, you're not going to make it go forward any more than you just pushing it yourself.
Right. They're not helping a bit, right? Not at all. What if they came up and they push it like this? Then you probably cannot keep it polite in that situation. Are they helping you? No, they're not. Not only are they not helping you, they're stealing your energy. That's what they're doing. They're making you waste energy. So this one is an example of they're exerting a force, and there's a displacement, but the force is not responsible for the displacement. Okay, the force is not responsible for the displacement. What they could do is they could push it like this. What do you think? Raise your hand if you think if they came and they pushed it like this with this last force I drew, would that be helpful? And if you think that would be helpful. Yeah, this person probably gets a thank you. They get a thank you. So this person, it's not as good as maybe pushing in the back, but when they push, their force is going to break up into pieces. And there's going to be, an X component and a Y component. And the Y component is doing no good at all, but the X component is in the direction of the motion and it's helping. Okay, so the idea is that the work is equal to the piece of the force that's in the direction of the motion times the displacement. So that if the force doesn't have a component in the direction of the displacement. I'm using delta x, but it doesn't have to be in the x direction. Whatever way it's moving, we want to find the component of the force in that direction. So just in general, if I have a displacement like this and a force like that, I would want to find the component of the force that's in the direction of that displacement. And so the way I would do that is I would define an angle theta between the force and the displacement. And then I would want this adjacent side to that angle, which would mean I need a cosine. And we could say the work is F cosine of theta times delta x. Now it's customary to kind of rearrange this and say F delta x cosine of theta. But this is the definition for work. So going back to our list of hard work. So, you know, some of these things, running at a constant speed, okay? If you're running at constant speed, then the forces on your body are, you know, there's a force of gravity and there's a normal force, but your delta x is like that. Now, if you had a forward, if your normal force is pointing forward, then you're accelerating. Okay, so normally when we're running constant speed, and that means these forces are canceling. And we're not really doing any work. Playing basketball, you're running around a lot, and you are doing work during the time that you're accelerating. So, you know, maybe we should accelerate a lot in basketball, right? Because you're always changing direction. So let's go ahead and say, you know, running at constant speed would not be doing work because your net force is 0 if you're running at constant speed. But when you have to change directions frequently, that requires work. Pouring concrete, if you're the guy driving the truck, the only force and displacement that you're directly involved in would be, you know, pushing a lever. You know, if you're spreading the concrete with a trowel or you know, maybe you're using a shovel to kind of scoop it around, then there would be some work involved there. So it really depends which construction job. The guy running the crane isn't actually doing a lot of work, and he's probably getting paid the most. You know, we could go through these a little more, but the point is, this one, the force must be responsible for displacement, makes a lot of things not turn out to be work in the physics sense when they still make us tired. Okay, let me pause. Any questions about the definition? This is our definition of work, our mathematical definition. Okay, now remember, energy is defined as the capacity to do work. What actually happens when we do work is we are transferring energy from us to something else. This person there, if we would put in the angle between their force and displacement would be 180 degrees because their force points to the left and the displacement points to the right. Cosine of 180, I'll write this down, cosine of 180 degrees is -1. So this person would actually be doing negative work, which essentially means I'm doing positive work, giving the car energy, and then they're doing negative work, taking the energy away from the car. So they're basically one step removed away from stealing my energy directly, which is why I would be so, you know, impolite to that person. Maybe, I don't know. Okay, so let's talk about what happens when we do work. I wanted to try to show you why work represents an exchange of energy. So just imagine we have some object. Could be just an asteroid in space, so no gravity, nothing, just floating there. And now I exert a force. And when I exert that force, there's going to be a displacement you know, in the direction of my force. The displacement doesn't always have to be in the direction of a particular force. There are more complicated pictures, but this is a good illustration. So I'm kind of making a simple illustration here. So then suppose I do work. So I could say, you know, the work is equal to the net, not the delta, the net force. This would be the net work, will be the net force times delta x times the cosine, in this case, of 0 degrees. And cosine of 0 is just 1. So the net work would be the net force times delta x. But we know, according to Newton's second law, that net force is equal to ma. So the net work would be m times a times delta x. But in our kinematic unit, we saw this expression a times delta x, that combination of symbols appeared in one of our master equations. So if you recall, we had v final squared minus v initial, or equals v initial squared plus 2a times delta x. That was our third master equation in chapter 2, our very first chapter. And I see a times delta x here. So I can rearrange this and have v final squared minus v initial squared equals 2 a delta x. And dividing by 2 on both sides, I get an expression for a times delta x. And that allows me to rewrite the formula for net work as m times v final squared minus the initial squared over 2. And if I do some algebra, I can split this into 1/2 m times v final squared minus v initial squared, or even 1/2 m v final squared minus 1/2 m v initial squared. And what I see is the final of a quantity minus the initial of quantity, and we can think of that as a delta. Delta of the quantity 1/2 m v squared. So when we do work, something changes. What is it that changes? This strange quantity, 1/2 m v squared. So we want to try to understand, what is this quantity? What is 1/2 times m times v squared? So I already asserted that when we do work, we are transferring energy from us to a system. In this case, this object, which has a mass m, when I do work, something about the object changes. And I want to see if we can interpret that as energy. So let's see if it makes sense, because remember, energy is the capacity to do work. So does something have the capacity to do work if it has a mass and a velocity? So let's just think about that. Suppose you have some object, like a bowling ball. It has a mass, has a big mass, and you take the bowling ball and you set it on the ground, so it's not moving. It can't really do any work if it's just sitting on the ground. But what happens if you roll the bowling ball? If you roll the bowling ball, it now has mass, and it has velocity. And raise your hand if you think of a bowling ball rolling down, let's say, a hallway on campus, if that would have the capacity to do work. You don't think so? I think if I roll a bowling ball down the hallway at the campus and some people walk out of their classrooms, I think the bowling ball is going to do work on the people walking out of their classrooms. I mean, let's put it this way, work is new. Can the bowling ball, when I roll it down the hall, can it exert a force on something? Raise your hand if you think the bowling ball could exert a force on something. Okay. Can it cause that thing to be displaced? Yeah, I mean, bowling would be pretty boring if bowling balls couldn't move stuff. And don't tell me you already think bowling is boring. I understand maybe some of you feel that way, but it would be even more boring. So now let's go back at this expression. Does a bowling ball have more capacity to do work the bigger its mass is? Raise your hand if you think the bigger the mass of the bowling ball, the more capacity to do work it has. Okay, how about moving faster? Does it have more capacity if it's moving faster? Yeah. Okay, so this little quantity does have some intuitive sense to it. If I have something that has a big mass and it's got to be moving. If it's not moving, it's not going to exert a force on me. But if it's moving and it bumps into me, it can exert a force. And the force is going to be bigger if it's more massive, and the force is also going to be bigger if it's moving faster. So we are going to give this thing a name. We call it kinetic energy. Remember, kinetic from friction means moving. So this is the energy associated with movement. Kinetic energy is defined as 1/2 times mass times velocity squared. And what we can say is when we do work, there is a change in the kinetic energy of the system. This is known as the work energy theorem. I don't know if we have to really call it by that name, but it sounds fancy. It makes us feel it's important. It is important. When we do work on a system, the kinetic energy of the system will change. Now, what we're going to learn, because energy can change forms, is that the work causes energy, kinetic energy to change, but that may almost instantly change into thermal energy or electrical energy or some other form of energy. For right now, we only know about one kind of energy. And we would refer to this work as mechanical work. And when we do mechanical work, we get a change in kinetic energy. Maria, was that an accidental hand?
Yeah, sorry.
That's okay. I just have to check to make sure. All right. So let's do an example of how this works. And I want to stress that this is fantastic. Okay, this work energy theorem, you are going to love it because energy is not a vector. Kinetic energy is not a vector. Work is not a vector. And if there's one thing that causes students a lot of trouble starting out in a physics class, it's vectors. I mean that, and now I know some of you are doing well with your vectors, but even though you're doing well, there's still a lot of work, okay? And so once we start learning about energy, we're going to discover that we can solve problems using energy that we would have solved using Newton's laws and our kinematic mass equations, all of that other physics. We can solve some of those problems directly using energy with no vectors really involved. So let me give you an example of that. So suppose we have, a box sitting on, the ground, and maybe we apply a force like that at a certain angle. And of course, we know that there's going to be a normal force, and there's going to be the force of gravity. And maybe there's even, let's do it with no friction first. We can add friction later. And so then there's a displacement. I'm going to draw the displacement in a different color so we don't confuse it for a force. Okay, so we have a displacement. Let's say it's 10 meters. And the force we are exerting This applied force, let's say it's just 50 newtons, and there's an angle of 30 degrees there. And I want to find, if it starts from rest, how fast will it be going after it travels 10 meters? So this is a problem. I could have put this on your last contest, and it wouldn't have been a very hard problem. How would we solve this on the contest? With or without friction? We would sum the forces in the x direction, find the acceleration in the x direction, and then we would go into our kinematic mass equations and try to say, okay, well, we know the initial, and we know the acceleration, and we know the displacement, and we want to find the final. We would figure out which mass equation to use, and we would use it, and we would solve. And we get 10 out of 10 on that problem. But we can also use energy to solve the same thing. So we just say net work equals change in kinetic energy. And the beautiful thing about using energy is that every single problem starts in the same place. I mean, in homework, there's a couple of problems that just ask you compute the work of this force. And it's not in the context of a larger scenario. But once you practice that, all of the word problems that have pictures and forces and displacements and things, that always start here. And it's very, very comforting to know where the problem starts. So this says add up the work from every force in the picture, and that's equal to the change in kinetic energy. So we simply have to list, we have a normal force here and force of gravity. So we're going to have the work done by the normal force plus the work done by gravity and plus the work done by the applied force, and that's equal to kinetic energy final minus kinetic energy initial. Now it looks like I'm doing math right now, but I'm really not. I'm just going through the logic of the problem. I'm not actually doing any math. I don't have to think about like if one of these guys might be negative, because they're not vectors. They don't have directions. So each of them is going to be a number. It could be a positive number or a negative number or zero, but that number is just going to come out naturally during the course of this problem. I don't have to think. I just write them all down and connect them with plus signs. Just add them all up. That's what the sum means. Then the delta KE is the final kinetic energy minus the initial kinetic energy. Okay, so I'm just organizing my thoughts, saying, okay, here are all the potential tasks ahead of me. But the beautiful thing is many of the terms in our problems are going to wind up being zero. Okay, so this is almost like just doing accounting. We have 5 different cash registers, and we have to just see if any of them were used. And if 3 of them were never opened, then we know that they don't really affect the balance of our, our money for the day. Okay, so for example, the initial kinetic energy, if the box had an initial velocity of 0, if the velocity is 0, the kinetic energy is 0. So I know there's no initial kinetic energy, and I can cross that out without ever writing down a formula or plugging in numbers or even caring what the numbers are. Other than that, we have 0 here. Okay, now I should give a mass on this box. I forgot to do that, but we need to know that. Maybe this is a 10 kilogram box. We will need the mass at some point. Okay, now final kinetic energy. Will there be final kinetic energy? Well, yes, because we're asking how fast is the box going to be going at the end. So we should assume it's moving at the end. Okay, so we're going to have that staying around. Now we go through all of our works. And remember, what do we need for there to be work? We need there to be a force, we need there to be a displacement, and we need the quote-unquote, the force is responsible for the displacement. So if we go back and look at our equation for work, we have a force and a displacement. If the force is responsible for the displacement, that has to do with what is the angle. And the only time there would be no work is if that angle is 90 degrees, like this one up here, okay? If we're at any kind of angle, even a negative, 180 degree angle, there's work, but only if the force is perpendicular to the displacement, there's no work. So in this case, the normal force is perpendicular to the displacement. Not only in this case, but almost always. The normal force is at a right angle to the surface, and the displacement is along the surface. So the normal force does no work. How about the force of gravity? Well, in this case, because it's level ground, the force of gravity is also perpendicular to the displacement, so it does no work. Okay, so far, I'm not doing any math yet. I'm just using logic, and after you practice this and you get the logic down, first time around it's not obvious when you can cross a workout, but after we do it a few times, it will be obvious. If the force is perpendicular to displacement, we can cross out that work. If the velocity is 0, we can cross out that kinetic energy. So this leaves me with only 2 out of the 5 possible terms. So all I have to do now is write down the formula. So work from applied force would be applied force times delta x times the cosine of the angle. And the final kinetic energy is 1/2 mv squared. And so the final kinetic energy would be related to the final velocity. And now we can check what we know. We know the applied force, and we know delta x, and we know theta, and we know the mass, and we know 1/2. So we can solve for V final. V final squared would be 2 F applied delta x cosine of theta. So V final is the square root of all of that stuff. 2 times 50 times 10 times the cosine of 30. Ziad.
So real quick, what happened to the mass that was next to the 1/2 and the V final?
What did happen to it? Did I forgot the mass. That's a good point. It should be here.
Thank you.
So that's not the right number. Thank you. Yeah, we need that mass. Keep forgetting that mass. So it's going to be 9.3 meters per second. Okay, notice the difference between this approach and using Newton's laws. With Newton's laws, I have to draw all the forces, which I did that anyway. I have to write down Newton's second law, split the forces into components, and figure out which component is most important. In this case, it would be the x component. I would solve for the acceleration in the x direction, and after doing all of that work, then I have a chapter 2 problem to complete. I have to go through and look at my master equations and try to figure out which one is the best one. And again, we're pretty good at that by now, so it would be an easy problem either way. But this, we are going to find this is tremendously easier, not only because we always start from the same place, but many of the terms just cancel out, and there's no quadratic equation here. There's no finding components. There's no tilting our head because of the angle of the ramp. There's no, there's a lot of things that we get away without doing. We never have to solve for time. In fact, that's a limitation here. This will never tell us how long it takes. It kind of skips. Using energy skips Newton's laws, and it skips finding time, and it goes straight from initial velocity to final velocity. Very, very powerful. Haley.
So I guess at the very beginning when you're saying how energy is not a vector, is that why we have like the force of gravity and stuff in there? We don't have to make that negative? Is that only in like these?
Yes. Exactly. When I write on the left-hand side the work from the normal plus work from gravity plus work from applied, I am not thinking in any way about the directions of those things. None of them are ever going to get a minus sign. They're all just going to add together. Now, let's say we added friction into this problem. Okay, so if I had a little bit of friction here, then I would have, work friction here. When we compute the work done by friction, it's going to be friction times delta x, and we're going to see examples like this. But there would be an angle of 180 degrees, if we think of our axes as being right here, between the positive x direction of delta x and the negative x direction of friction. And that cosine of 180 is going to give us a minus sign. So minus signs are going to happen naturally when we start putting in angles. But we don't have to think of that. That's not necessarily thinking about it as relating to vectors. It's just there are angles between these vectors, but we don't ever have to find components of the vectors. Okay, good. Did that answer your question? I'm going to assume it did. Okay, so any other questions about this problem? Okay, let's do one more and then we'll take a short break. Okay, so suppose we have an inclined plane and we have a box sitting on the inclined plane. And we want to know how fast the box is going to go when it gets to the bottom of the ramp if we let it slide. And maybe the initial velocity is 0. We might have a 30-degree angle here, and our forces would be there's a normal force and a force of gravity. Okay, so that's what it looks like. And then we're going to have a displacement. Here, let's do it this way. I'm going to draw the displacement from the back of this thing because I can see the back of it moves a certain distance. So that displacement is how far this thing travels. And suppose we say delta x is 2 meters. Okay, so we have a 2 meter long ramp with no friction. We can always add friction in later. And I'm drawing the displacement in a different color so we do not confuse it with the force. And I want to find how fast this is going. So I start with net work equals change in kinetic energy. And in this case, we had only 2 forces, so we're going to have 2 works. That's going to be work from gravity plus work done from the normal force. And that's equal to KE final minus KE initial. Now we go through these one by one, and we just ask, can I cancel them? So we start with the work done by gravity. Can we cancel it? Well, we can cancel it if it makes a 90-degree angle with the displacement. And this angle there, that's not 90 degrees. Okay? So we cannot cancel out gravity. How about the normal force? Does it make a 90-degree angle with the displacement? Yes, it does. So I can cancel that out. And that's going to be largely true of normal force in virtually every problem. How about the final kinetic energy? Can I cancel it out? Well, remember, cancel out if the object's not moving at the end, but it is moving at the end, so I cannot cancel it. How about the initial kinetic energy? Starts from rest, so I can cancel out initial kinetic energy. Now we just write our formula for work. That's going to be the force. In this case, the force is called Fg, times delta x, times cosine of theta, equals, on the right-hand side, we have just 1/2 m v final squared. Force of gravity is mg. And in this particular problem, we see that the mass cancels. It cancels a lot, which is why probably I forgot about it on the last problem. So if I want to find the final velocity, I just multiply both sides by 2. And we have v final squared equals 2g delta x cosine of theta. Okay, so v final is the square root of all of this. I want you to go ahead and plug the numbers in on your own and get your answer. I'm going to wait just a minute and then I'll do it. You go ahead, plug in the numbers, and even if you don't have a calculator, plug the numbers in, and then you'll see the final answer when I use my calculator. Okay, raise your hand if you got an answer. Okay, I'm going to do a little poll, and I want to see what answers you got. So pick answers 1, 2, or if you got something else, pick other. Okay, so what we had as options were 5.83, 4.43, and other. And the votes were 7 here, 1 here, and 2 here, with 2 no responses. So let me put the numbers in. We should have 2 times 9.8 times 2 times the cosine of 60, and that equals 4.43 meters per second. And I got you all, because I'm the one who picked 4.43. I got you all with a very common mistake. Okay, this is an evil mistake. It's an insidious mistake. You guys mostly put 30 here, and that's how you got that number. But that is not correct. Does anyone see now that I say the angle should be 60 degrees, can anyone see why it should be 60 degrees? Okay, so here's the problem, okay? And I wanted you guys to all make this mistake now so that you can avoid this mistake in the future, because this is the one place where we're still going to struggle a little bit, with the remnants of vectors. Dustin?
Sorry, I didn't mean to do it, but it's the.
Oh.
I didn't mean to click that, but it's because it's the exterior angle, right? Not the interior angle.
Well, why is it the exterior angle? You're talking about this angle up here, I think.
Right.
Or
Isn't that
here.
because that's right? That's the angle with the displacement, the 60 is.
Exactly. So we want the angle theta, but we don't want any angle theta. We want the angle between the force and the displacement. So for the normal force, that angle is 90 degrees. For the force of gravity, it's 60 degrees. If there were friction, then it would be 180 degrees. Each force should have its own angle. So to avoid making that mistake, we could call this theta g. And that might help remind us that it's not any old angle. Here's the problem. Why we all, including myself the first time I did this, I'm sure, make the same mistake. It's because we call every angle we meet theta. Okay, and so when I see a theta in a formula and I see a theta, in the picture, my brain immediately links them together. But it's very hard when we call two different things by the same name for us to psychologically separate them. This is just part of the way our brain works. So by calling every angle I meet theta, I'm really setting myself up for disaster, just like if I call every mass I meet m, because then I lose track of which one is really m1 and which one is m2, or ma and mv. Same kind of thing. So going forward, when I write down angles, I don't really want to just write theta. I want to write theta something to help remind me which theta I'm looking for. Because this is such an easy mistake, common mistake to make. And it's just a remnant of vectors, because there are still vectors here. Force of gravity and delta x are vectors, and we need the angle between those two vectors. Okay? So aside from that one little problem, that little glitch of possibly getting the angle wrong, this is an incredibly easy problem. Even though today is the first day you ever saw, probably for many of you, the work energy theorem, or heard about kinetic energy or work in this context, you would probably still say this is easier than what we already practiced for a week, which is to take this picture, to, rotate the picture, try to, okay, I went a little overboard on the rotation. You know what I'm talking about. That whole process, rotating the picture and then finding the x component of the force of gravity, which actually goes with the sine of the angle instead of the cosine. And, there's a lot of problems, and there was a lot of difficulty for us to learn how to work with the inclined plane. We had to learn tricks. There's no trick here. It's one basic equation, and I apply the same basic rules to that equation that I apply to every single problem, and without any kind of trickiness, without any special rules, I get to the answer. The only thing that was tricky was that angle, and that's a mistake. We shouldn't make that again. We should just make it today, and then we never make that mistake again. Okay, any questions about this problem? Okay, let's take a short break, maybe 5 minutes.